Today's lecture, we study some previous concepts about baseband communication, and later on, we study bandpass communication. You know, all real world signals are analog in nature, especially voice and video. Digital devices like computer generate digital data. For real analog signal, we need analog to digital conversion to convert data into the digital bit stream. So finally, data from all sources come into 1 and 0 form. So this 1 and 0 form cannot be transmitted over the wireline medium until or unless it is represented by some voltage levels. So the representation of these voltage levels is called binary signaling. For example, in 1 gigabit Ethernet, we use 10 by 8 by 10B coding scheme. So normally in binary signaling, we use two symbols for communication, and symbol rate is equal to the bit rate. But we want to improve the data rate and to improve the bandwidth efficiency, we need m greater than 2. So we need more symbols for transmission. It means one symbol represents multiple bits. So what will happen that if k bits are representing one symbol, so the bit rate divided by k symbols is equal to the symbol transmission rate, and the value of k is equal to the log 2 m. So for m greater than 2, we use pulse amplitude modulation, and for m is equal to 2, we use different line codes. So in baseband communication over wireline medium, we have a different selection criteria of line codes. And these selection criteria include self-synchronization, low probability of bit error, spectrum suitable for the channel, power spectral density, transmission bandwidth, and transparency. So self-synchronization means that we have multiple variation during the bit pattern, and these are used to extract the timing information. And also the performance of line codes will be improved by having low probability of bit error. Because there are consecutive ones and zeros in the bit stream, and we use particular coding schemes for removing these consecutive 1 and zeros. Spectrum suitability depends upon that at zero frequency we have non-zero values of the line codes. Otherwise, it is not suitable for communication over the channel. So power spectral density determines the transmission bandwidth, and if it is bandwidth efficient, so it is more suitable for transmission. But the bandwidth occupied by the line code depends upon the variations in the line code. And these variations helps in one way but trouble in other way. So Also, the last factor is the transparency, which is that how correctly we can recover the bit pattern at the receiver. So whether we are using m is equal to 2 or m greater than 2, so we are using one-dimensional constellations. So this is the review of line codes and PCM waveform patterns. These are used when we are using m is equal to 2. So there are different patterns for 1 and 0, and there are a number of line codes to represent these patterns. So you may consult any data communication book for the these patterns, that how can we draw these patterns. So for example, I'll take a biphase level. So biphase level is very common and it has half bit duration. And in this, you can see that we have positive to negative and negative to positive for 0. So this high to low and low to high bit pattern for half duration help in synchronization, and it is the most popular one, line code. So you can take the random bit stream and just like we take here and try to draw these patterns. As far as the normalized bandwidth versus spectral density, watt per hertz is concerned, so we can see that the Dobbin ray coding and NRZ have non-zero values at 0 frequency, so they are better in performance. Also, we can check that the bandwidth occupancy of different line codes like biphase code has more bandwidth occupancy than the other line codes. So you can check the bandwidth and the frequency nulls at this power spectral density of line codes. For m greater than 2, so we use pulse amplitude modulation. So the pulse amplitude modulation is used for m greater than 2, and we can see that how can we use pulse coded modulation for m is equal to 2. So this is used to increase the bandwidth efficiency of the code, because you know the Nyquist criteria is that maximum transmission rate is 2 symbols per second per hertz. So we cannot transmit 2 symbols per second per hertz without ISI. So to increase the bandwidth efficiency, we need to map multiple bits with the symbol. So in that way, we can improve the bandwidth efficiency of the code. So the bandwidth efficiency is in fact is the data rate divided by the bandwidth, which is bits per second. So now look at pulse amplitude modulation. The pulse amplitude modulation is in fact is 8 level. So we have a random waveforms. So these are 5, 7, 5, 2, 3, and 1. So these are randomly generated and represented by different voltage levels. So these are the pulse amplitude modulated pulses having 8 levels. So this is in fact 8 array communication But how can we represent it in binary? So in binary, we use PCM waveforms. So in PCM waveforms, this one symbol use 3 bits, because if we want to generate 8 symbols, so we have to map 3 bits per symbol. So each symbol is represented now by 3 bits. So the bandwidth efficiency of this binary signaling is lower than this uh, pulse amplitude modulated M-ray signaling, which has 8 symbols. So after baseband modulation, we applied pulse shaping. So you can recall or study the previous lecture in which we used pulse shaping. After pulse shaping, we have a sync-like pulses, or the duration between these pulses is T, and they are consecutively transmitted from T0 to T6 time. So why we use passband modulation? So passband modulation is used for longer distance transmission, just like we have Ethernet, but the distance is not very long. But we have to use modem to transmit 64 kbps over a telephone copper wire. So in that case, we need QPSK modulation. So this QPSK modulation is also used for wireless transmission. So this is in fact is digital passband modulation. In digital passband modulation, we have in-phase component and quadrature phase component. So in-phase component is along the x-axis and have cosine represented by the cosine carrier, have positive and negative amplitudes. And similarly, we have the quadrature component, which is the imaginary component, and have the representation by the sign positive and negative. So passband modulation occurs after baseband modulation. So that is the important point, that we perform line coding before passband modulation, because first we generate the voltages, then we transmit it over, we map it over the symbols of for digital communication. So this mapping of bits over the symbol is called passband modulation. So, but normally we use baseband equivalent model. Baseband equivalent model is used because modulation is multiplication with the carrier, and demodulation is also multiplication with the carrier to phase recovery. So this modulation and demodulation is transparent during the entire communication, and we need to study the baseband equivalent model. So we skip the modulation and demodulation stage at both transmitter and receiver, and we learn all the digital communication techniques over the baseband equivalent model, which is equalization and pulse shaping. So this is an example of the baseband equivalent model for digital ASK modem. So in this, we focus on this part. So this part is in fact includes analog to digital conversion again. So the same way we perform the analog to digital conversion before transmission, we need analog to digital conversion here. Why? Because the received waveform is analog in nature. So we have a sampler here to sample the analog signal, and then we have a decision making stage which have the decision boundaries for the signals. For example, for 8 PAM, we have the decision boundaries of 8. Uh, so so it is a sort of quantization that the sample we take, we will quantize it to assign different levels as quantizer do. So the decision making is depends on the quantization method. So this all together, sampler and quantization, sampling and quantization will is in fact is the analog to digital conversion, right? So, so here, as I told you before, that we uh, apply pulse shaping after baseband modulation, and then we perform passband modulation. So you can see an example that this is the pulse shape which we modulate and looks like this. So, for example, we have the root raised cosine pulse with roll-off factor r is equal to 0.5, and after multiplying with a cosine carrier, so we have a waveform like this. But the peak value is lies some point at the middle sample, and that is equal to 0.719. So the same you have here. The same you have here. The situation, the same is here. You have the value 751 and the peak value is 0.715. So, but the amplitude varies. The amplitude varies like this. So it is, this variation is according to the pulse, but it is extended in negative side as well. As you see here that it is extended at negative side as well. So what is necessary, maybe the negative part is not necessary. We will take a look of the positive part and try to recover the uh, waveform of the signal, and or we try to detect the symbol by matching it with closely matched sample values as we have studied in match. So this is about the pulse shape, but I also experiment over the random data. I have chosen a random data of length 20, and I have a root raised cosine pulse shaping filter of 0.5, and I multiply it by sine carrier, and I see that this is the waveform is the same we have discussed here, that the negative size is not important. So the waveform represents the signal at the top is important for us. We study later on that what is the waveform which is slow varying waveform at the top of the signal. What is this? And how can we recover this waveform. So we will learn later on in the lectures. So the signal, what is the significance of this signal? So maybe we increase the signal energy and we may able to transmit it for a longer distance. So before we study the passband modulation, so we represent the signal representation. Here A of t is the amplitude and theta of t is the angle. So either we change the amplitude or we change the angle. So we can modulate this carrier signal by its amplitude or by its angle. So angle contains the frequency and the phase. So either we change the frequency or we can change the phase of the signal. So on the basis of it, amplitude variation reflects amplitude shift keying, phase variation represent phase shift keying, and frequency variation reflects frequency shift keying. So this is the magnitude and phase representation of the signal, but we can have another representation of the signal, which is I and Q representation. I is for in phase component and Q is for quadrature phase component. So cosine omega naught t is in fact this component is split by trigonometric identity, and we have separated the two terms among this is a cos of phi and a sine of phi. So a cos of phi is in fact is the x of t, which is the in phase component, and we have y of t, which is the quadrature phase component, and the signal is represented in I and Q form. So this is in fact is the I and Q form of the signal, that we have x of t cos of omega naught t minus y of t sine of omega naught t. So basically the advantage of in phase and Q phase component is that in phase and Q phase component are orthogonal. So how can you check it? You multiply this cosine of omega naught t with sine of omega naught t, and you will check that they are orthogonal to each other if the answer is 0. So simply you generated the cosine carrier and sine carrier in MATLAB with the same sampling frequency, and you will see the result is 0. So another advantage of this, you can transmit parallel over in phase and Q phase component. You divide the bit stream into parallel streams, and one is modulated by in phase component, other is modulated by quadrature phase component. So by doing so, we can save half of the bandwidth, because here we are not changing the frequency of the carrier, because the cosine component and sine component have the same carrier frequency. So how can we calculate the amplitude? We can calculate the amplitude by squaring the x and y component and take the phase by taking the tangent first, y of t by x of t. So after we get the amplitude and phase, we are reproduce it in magnitude and phase part. This is a of t and this is phi of t. So we are able to reproduce it in magnitude and phase part. So you can see that the in phase component and quadrature phase component are orthogonal. This is mathematically you can prove. So you can split x of t here and multiply 2 here and divide by 2 here. So 2 cos of omega naught t sine of omega naught t will be equal to sine of omega naught t minus omega naught t and sine of omega naught t plus omega naught t. So sine of 0 is 0 and all the multiples of 2 pi are also 0. So the result will be 0. It means that this I and Q component are orthogonal to each other. So you can detect the signal on the basis of two basis function and you can modulate the signal on the basis of these two I and Q basis functions. So the complex envelope representation is also important, and we take the magnitude and phase representation of the signal for this. So we know exponential has two components, the cosine components and the imaginary component is the sine component. So if we take the real of this, so it is the cosine component. So the real of this is a e j omega naught t. So we split this phase into omega naught t and phi component. So this will be the product. So aej phi is a separate component and this aej phi is equal to g of t. So this g of t is called the complex envelope of the signal. So this ej omega naught t, the real of this is in fact is the cosine of omega naught t, which is the carrier component. And this EAJ phi complex envelope is the message. So the message is in fact is the AEJ phi component. So we can see here that the top of this signal is in fact is the complex envelope. This is the red waveform. The top of this is in fact is a EJ phi. EJ phi, right? So this is EAJ phi. So this is equal. This is called G of t, and we try to recover this G of t. So this G of t is the complex envelope of the signal. So we cannot have, we can have the magnitude and phase representation of the waveform by taking the magnitude of this complex envelope is the amplitude and phase phi is the angle G of t. So this G of t will easily translated in the back into this magnitude and phase part by putting A as the magnitude of G of t and phi as the phase of G of t. So there is a relationship between complex envelope and I and Q representation. So the real G of t is the x of t and imaginary G of t is the y of t. So g of t is aej phi. So the real of this is a cos omega naught t, and imaginary of this is a cos phi, and this is a sin phi. So we can also do it by expressing it aej phi as x of t plus j of omega t and the product of this. So you can multiply the real with the real and imaginary with the imaginary. And this will give you the relationship x of t omega naught t minus y of t sine of omega naught t. So this is the complex envelope representation. The signal in complex envelope. So this is in fact represent the spectral attributes. So if you have the Fourier transform of this, so in fact what you are doing, so this is a cosine. So this cosine is shifting the signal g of t at minus f naught and plus f naught. So it is in fact is transforming the signal g of t to this cosine, which is in fact is at minus f naught plus f naught. Because the Fourier transform of this ej omega naught t is two impulses with half of the magnitude. So when the signal g of t is transformed in Fourier domain, so it is g of f. And when g of f multiply with two impulses with weight 0.5, so you will get this signal. So now there is other thing I need to mention before starting passband modulation is in fact the confusion about the symbol energy and symbol duration. So there is a relationship between the amplitude and the symbol energy and symbol duration. So you can simply see that amplitude can be written in the form of under root 2 ARMS, right? So, or if we take the ARMS square, so it will be the square root of 2 ARMS square. And ARMS square is in fact is the power contained by the signal. Now, what is power? Power is the rate of change of energy, or the rate of change of energy if the signal is periodic. So we take its power. Otherwise, if the signal is limited, so we take its energy. So for a periodic signal, we take the rate of change of energy, which is E by T. So we have the energy for one symbol is E by T, which is the power of the symbol. Also, we can interpret it in this form that power is equal to the voltage square divided by resistance. And in communication, we take resistance value is equal to 1 ohm. So power is equal to V square. So here you have seen that we will take the power is equal to V square, and V square is in fact is the energy of the signal divided by bit duration. or symbol duration. But the total energy contained by the signal, both in a time domain or frequency domain, is equal. So this is in fact derived by Parseval's theorem, or here x of f square is in fact is the power spectral density of the signal. So because there is some confusion that we take it as energy spectral density or power spectral density, because if we consider the signal periodic, so we take the power spectral density. So if we consider the signal as time limited, so we consider its energy spectral density. So the periodic signals are power signals. So there are a number of modulation schemes we have discussed before, ASK, FSK, and PSK. But the other is the hybrid technique, in which we change the amplitude and phase. And that variant is called QAM. That variant is called QAM. So it supports data rate up to as a symbol up to 64, which means that it has a very denser constellation. Or the QAM64 constellations are very complex as well. In fact, you have a variety of options for these constellations. The binary variants are this. These binary variants all are one-dimensional. So if the Euclidean distance is same, then the probability of bit error rate of BASK and BPSK is same, but BFSK we consider the probability of bit error for binary signaling. For m greater than 2, we need to use M-array modulation schemes. In M-array modulation schemes, you can see that we have the ASK, in which we have a non-constant envelope. So the envelope is non-constant. We transmit the symbol with 0 for the presence and 1 for the absence, or vice versa. So the decision boundary is here, and it is one-dimensional with a single basis function. So the other is, in fact, is the phase shift keying. In phase shift keying, we have the constant envelope, but we have the abrupt changes in phase. For even a very denser constellation, we cannot avoid 180-degree phase changes. For this, in assignment, I gave you QPSK, OQPSK, and other variants to study that how can we avoid these abrupt changes of the phase. So next is the frequency shift keying. In frequency shift keying, we have constant envelope, we have continuous phase. It is orthogonal signaling with n dimensions. In PSK, we have 2 dimensions, but in FSK, we have n dimensions. All these n dimensions are generated by orthogonal frequencies, and all these orthogonal frequencies are integer multiple of each other. So that's why, because they are the integer multiple of each other, so all these starts from 0. And if you generate carrier by different uh, uh, integer multiple of frequencies, so all these are orthogonal, and the cross correlation of this is 0. So that is why this looks similar to orthogonal signaling. But as far as the detection is concerned, we need modulation and demodulation. So this is in fact the modulation is in fact we have discussed earlier, and the modulation is divided in two parts: coherent and non-coherent. In coherent, we need the phase information. In non-coherent, we don't need the phase information. So this can be treated as the different variants with binary, emery, and hybrid. But the important thing that the PSK uh, don't have the non-coherent version except DPSK, right? So we will study the demodulation of these schemes which are left in your previous study. So previously you have the theoretical bit error rate performance of these digital modulation schemes, but now we will tell you how we have the receiver architecture on the basis of what we have learned so far, right? So here I finish my lecture. Thank you very much for joining.